This video is running through an overview of geometric models for recursion financial modelling in further mathematics. So firstly, just a quick recap, geometric growth and decay. So when we're looking at geometric models, we're talking about each successive term in a sequence being found by multiplying by a constant value. So when we're looking at something that is growth, the increase, that means that that value of the multiplier, shown here as the capital R, is greater than 1. If we have decrease or decay, that value of R is between 0 and 1. And so the common applications that we look at in further maths are reducing balance depreciation and compound interest loans and investments with no payments, just interest. And geometric growth, a reminder here that we have our recurrence relation form. So as we said, each of our recurrence relations will have an initial value, and then we have this multiplier R. Moving to a general rule form, we take that initial value and value of R into this format where we have Vn equals R to the power of n times V0. So in our example here, we have S0 equals 10, and our recurrence relation Sn plus 1, so the next term, is equal to 2 times Sn, or the current term. So the first 4 terms of this particular sequence, starting with 10 as our initial term, then our next term will be 2 times the current, so 2 times 10, 20. Then again, 2 times the current, so 2 times 20 gives us 40. And finally, 2 times 40 gives us 80 for those first 4 terms. So there we have 10, 20, 40 and 80. We can see there the graph of a geometric sequence has that exponential form. So the terms get very large very quickly when we're experiencing growth. Moving now to converting that recurrence relation into a general rule form. So again, we're taking our initial value and our value of R and substituting into the format for our general rule. So in this case, we would have Sn is equal to 2 to the power of n times 10. And so now when we're finding S8, we're substituting the value of 8 into each space where we're seeing n. So we'd have 2 to the power of 8 times 10, and that gives us a value of 2,560 for S8. A most common application of geometric growth is looking at compound interest. So in this case, our balance in our account, whether that's an investment or a loan, is increasing by a different amount each time period. So you can see here the recurrence relation form and the general rule form are exactly the same as they were for just our general geometric growth. A couple of key things that are, or terms that are a little bit different here. V0, our initial value, is often referred to as the principal. So the principal amount that was either invested or borrowed. When we're calculating R, because we do have growth, we are always working with 1 plus our rate. And you note there that we are talking sometimes about a rate per annum that is being compounded at multiple times per year. So we're just using that little c to represent the number of compounding periods per year. And it's very clearly stated in a question. And Vn is the value of that asset or that loan or investment after n time periods. So you're looking for keywords or phrases as compound interest or compounding, monthly, annually, things like that. You will see a rate of growth that's exponential. And our first job when we're doing questions like this is to identify R first and make sure it is an increasing value so that you've done 1 plus the interest rate. Moving now to some exam question examples of compound interest. We firstly have Manu investing $3,000 in an account that pays interest compounding monthly. The balance of his investment after n months, Bn, can be determined using the recurrence relation, B0 equals 3,000, Bn plus 1 equals 1.0048 times Bn. The total interest earned by Manu's investment after the first 5 months is closest to. So when we are calculating our interest, that is the difference between the value of the account and our starting point, so our principal value. So firstly, what we want to know is what is our value after 5 months. So what is the value of Manu's account at B5? And then to get our interest, we will be taking our B5 value minus our initial value, our principal of 3,000. So we're going to have a quick recap of how we do those type of recurrence relations using our calculator so that we can get that value of B5. Okay, so we're entering our recurrence relation into our calculator. The first step is always to enter our initial value. So B0 was given to us as $3,000 and we press enter. And then we type in our recurrence relation as we read it. So 1.0048 multiplied by, and this is where we pick up our answer using control and minus to pick up the previous answer and press enter. So after 1 month, we have the balance of $3,014.40. After 2, 3, 4, and 5 months. So each time just pressing enter or equals to get the next value in that sequence. So we can see after 5 months, Manu has $3,072.69. So we can go back now and calculate the interest. And so we see there $3,072.69 minus $3,000, the initial amount, left us with $72.69. So answer option D. Now next example, we have Ray has deposited $5,000 in an investment account, earning at the rate of 3% per annum, compounding quarterly. The rule for the balance Rn in dollars after n quarters is given by. So firstly, we want to work out what is our value of R. We are increasing, growing our investment, so 1 plus our rate of 3. It's compounding quarterly, so divided by 4, and all of that over 100. So that gives us an R value of 1.0075. So when we place that together, and we're being asked for just a rule, not a recurrence relation, so we're looking at the general rule form. Remember our general rule form? So in this case, we would have R to the power of n times different R, 0. They've written it with the first initial term first, but we're still looking for those two key components. So we would be saying that our best answer here is D, where we've got 5,000 times 1.0075 to the power of n. N represents each quarter. In our next example, Jen invests $10,000 at an interest rate of 5.5% per annum, compounding annually. After how many years will her investment first be more than double its original value? So we're being asked to find here when, so we need to find n, where the value is at least $20,000. So at least 20,000 because we started with 10,000. So let's make a general rule so that then we can solve for that n, how long it's going to take. So firstly, what is our multiplier? What is R? So 1 plus our rate, 5.5, and that's compounding annually, so I don't need to adjust. I can just divide by 100. So that means I've got 1.055. For my general rule, I have Vn is 1.055 to the power of n times my initial value of $10,000. And so I'm saying that I would like that to equal 20,000, and I would use my calculator to then help me solve for n. So it may be that you might like to note down that that's what you're entering on your calculator. So when I do that, I get n is 12.95. So in this case, we need the value to be more than 20,000, so that I would have to round that off to 13 years in total, because at 12 years, I won't quite have reached the target of $20,000. Our next example, the value of a compound interest investment in dollars after n years, given as Vn, can be modelled by this recurrence relation, where V0 is 100,000 and Vn plus 1 equals 1.01 times Vn. What is the interest rate per annum for this investment? So this time we're going to use the fact that we have that value of R and find what must be the rate per annum. Okay, we've been told it's in dollars compound interest per year, so we can assume there's no adjustment needed there. We know that R is 1.01, and we would solve for little r, our rate there, and we get a value of 1. So that's telling us it's 1% per annum. Now that's actually a value you might have been easily able to identify from the multiplier, but if it's a more complex number or you're not quite sure how and why it's 1%, we're using that rule there to solve, and that will work in any instance. At this point, it's good to talk about effective interest rates. So effective interest rates are when we're comparing the difference between the per annum interest rate that is quoted to us and what is the impact or what effect does it have that we are compounding more often than just annually. So typically we're given those interest rates as a rate per annum, and they are sometimes known as a nominal interest rate. Effective interest rates is when we are restating that nominal rate and expressing that as an equivalent interest rate if the compound interest was payable annually. So we're going to have a look at a little example as to what that looks like. When we use effective interest rates, it's when we want to compare different products, so different interest rates that are compounding over different numbers of periods per year, and being able to work out, well, what is the better deal depending on whether I have a loan or an investment. So how do we come up with an effective interest rate? For example, if I borrowed $10,000 at a compound interest rate of 6% per annum, and I want to think about, well, what is owed at the end of 1 year? If that loan was compounded annually, then my rate would be, my capital R value would be 1 plus 6 over 100. And so at the end of 1 year, I would have $10,600 in the account or owing on that loan. If, however, the loan was compounded monthly, that would mean my rate, my multiplier is actually R as 1 plus the 6% over 12 months over 100. So I'm getting a smaller rate, but it's being applied 12 times through that first year. And remember, your compound interest is calculating the interest on the balance at each time period, so each month in this case. So that means at the end of the 12 months, I would actually owe $10,616.78, so slightly more. If I take that value and convert that back to, well, let's pretend it was an annual interest rate compounding annually, I've been charged $616.78 interest, and that equates to a rate of, or an annual rate of 6.17% per annum. You can see some calculations here to give you some more detail about how I got those values. So basically what we need to understand is that the more often a rate is compounded, so the more compounding periods in a year, the amount of interest accumulated also increases. So for an investment, that's good news. But for a loan, that's bad news. It means I end up owing more in the same time period. We do have a formula for calculating effective interest rates from the nominal, but we have a function on our calculator as well, and that's what we want to always be using to convert between either the nominal or effective rates. Okay, so we'll use this first example here to show how we can utilise our calculator, but also have a bit of an understanding about the effective rates. So Daniel borrows $5,000, which he intends to repay fully in a lump sum after 1 year. The annual interest rate and the compounding period for 5 different compound interest loans are given below. And so we're going to be asked to compare these 5 options and decide when fully repaid the loan that will cost Daniel the least amount of money. So which option is the best option for him? Before we look at how to calculate or how to convert these rates to effective rates on our calculator, just something to note. Here where we have same compounding periods, okay, so we've got a set of compounding periods all weekly and different interest rates to compare. Because this is a loan, we want the cheapest outcome. So we want the lowest effective rate overall. So before I even have to think about calculating anything, I can see from those first 3 options, loan 1, 2 and 3, that loan 1 will be the cheapest. The reason being, if the compounding periods are the same, then the rate itself will dictate which is the best outcome or the best option if you want the least amount of money. So 12.6% per annum compounding weekly is going to give him a better outcome at the end than 12.8 or 12.9. Difference with loan 4 and 5 is that we have different rates, but now we're comparing quarterly compounds. So we need to consider the difference or the impact of quarterly versus weekly compounding periods. In general, if those rates were the same, but the compound periods were altering, the more often that something is compounded, the more interest that will be added to the balance. So in a loan, that's bad news. We want less compounding periods. Problem is here though that those rates are different. So let's have a look at some of them in our calculator to compare. Okay, so we are wanting to go into our finance menu and looking at interest conversion. So here we can either go, if I've got an effective rate, I can convert that to a nominal, or if I've got an annual per annum rate, or a nominal rate, I can convert that to an effective. So that's what I want to do this time round. It will bring up in my calculator that little EFF. So you can actually type that as well. So the first loan was 12.6% per annum, and that was compounding weekly. So we put in our rate, comma, the number of compounding periods. So if we press enter, we get an effective rate of 13.41. Now I said to you that the more compounding periods, the more expensive a loan will be, okay, or the higher the rate with the same compounding period. So just to compare loan 2, we can see there we've got a higher effective rate. So the rate itself changed, went up, the compounds stayed the same, but the effective rate increases there. So we're really wanting to compare loan option 1 and option 4. So option 4 was 12.7% per annum and compounding quarterly, so 4 times a year. So when we look at that there, we've got a rate, an effective rate of 13.32 compared to the best of the weekly options, 13.41. So the best option for Daniel is loan option 4. So comparing all of the effective rates there, as we said, D, loan 4 is the best option. Another example of what we could be asked to do with effective interest rates, we have Millie has invested $20,000 in her account at a bank with an interest compounding monthly. After 1 year, the balance in Millie's account was $20,732. And so we're asked to find here the difference between the rate of interest per annum used by her bank and the effective annual rate of Millie's investment. So we can firstly find the effective rate by looking at that 1 year worth of increase. So if we know that our rate is generally found, so our value at the end of 1 year would be the initial value multiplied by 1 times our rate over 100. And we've been told that that value at the end of 1 year will be $20,732. So we can use that to find that effective rate. So if we were just to treat it as 1 year. And so when we solve that, we get R equals 3.66. So that is our effective interest rate. So the compounding has been happening monthly, but we've just looked at the impact of the interest over 1 year period. We now want to compare that to, well, what is the nominal rate? Okay, so if that's our effective, we want to convert to nominal. And we'll jump to our calculator to have a quick look at that. Okay, so when converting to nominal, again in that same finance interest conversions, but this time we're picking up nominal interest rate. The NOM represents nominal. We enter those values in the same way. So we had said the effective rate was 3.66 and it was compounding monthly. So we put 12 times a year. And that gives us a nominal rate of 3.6% per annum. So we can now find the difference between the effective and the nominal, and that gives us an answer of 0.06%. And so as we said, our answer there, when we subtract the effective and the nominal, 0.06. So that gives us option B. Moving now into geometric decay. So here's where we're looking at decreasing values. Please note here, our recurrence relation and our general rule are exactly the same as they were for all of the growth examples. And so it's important to remember that when we're calculating that R value or identifying it, we're looking for a value that is between 0 and 1. So calculating it means we're doing 1 minus the rate over 100. And so here with our example, if we've got A0 is 100, AN plus 1 equals 0.5 times AN. So that's telling us I'm starting with 100. My next value will be 0.5 times the current term. So that gives me 50. Again, 0.5 times the current gives me 25. And finally, 0.5 times 25, 12.5. So the first 4 terms of our sequence there, 100, 50, 25, 12.5. Again, when we're looking at the graph of these sequences, we can see that there is that exponential style getting smaller, very small, very quick. And we actually will find that that graph will approach 0 but never quite hit it. So the terms in that sequence will get very, very small but never drop below 0 or to 0 itself. When we convert to our general rule, so again we're picking up our initial term and our multiplier R and substituting those in. So for our example here, we would have AN is equal to R, so 0.5 to the power of N, and times our initial value of 100. So when I have to find A8, I'm substituting 8 into both places. So 0.5 to the power of 8 times 100, and that will give me a value of 0.390625 for that A8. So our key application of geometric decay is reducing balance depreciation. So previously in linear modelling, we've looked at unit cost and flat rate, And now we're looking at that reducing balance style, which means my value of my asset is decreasing by a different amount each time, generally given to me as a percentage of the current value as opposed to the initial value. So be careful that you are looking for the key phrase or keywords, reducing balance depreciation. And when you are calculating your value of R, your multiplier, we are decaying, so we want a minus, 1 minus the rate. Sometimes we do have depreciating at multiple periods in a year, so monthly or quarterly, but generally speaking we are just doing annual, but just remember you may need to adjust that rate. And so just 2 examples to have a look at this reducing balance depreciation. If I have a truck that was purchased at $134,000, using the reducing balance method, the truck is being depreciated by 8.5% each year. Which of the following recurrence relations could be used to determine the value of the truck after n years, given as Vn? So you're looking for those keywords, reducing balance method of depreciation. And so firstly, what we're going to do is identify, well, what is my value of R? So 1 minus my rate at 8.5 over 100 gives me a value of 0.915. And the form of my geometric decay should be Vn plus 1 is the multiplier R times my current value. And so the one that matches this will be answer A in this case. So we have B0 is the initial purchase price, $134,000, and we have the correct multiplier there for R. This final example, despite it being a multiple choice question, is actually multi-step and using depreciation. So the value of van purchased for $45,000 is depreciated by K% per annum using the reducing balance method. After 3 years of this depreciation, it is then depreciated in the 4th year under the unit cost method at a rate of 15 cents per kilometre. The value of the van after it travels 30,000 kilometres in this 4th year is $26,166.24. The value of K is what? So we want to work out what was the rate for the reducing balance method. To be able to do that, we first need to know, well, what was the value of the van after 3 years? So we've had a change in conditions here. We've been doing reducing balance, and then the 4th year we did unit cost. So we're going to need to work backwards from the 4th year value of $26,166.24 to get a 3rd year value, so that then we can just concentrate on the reducing balance. Okay, so our 4th year value, so let's say V4, would be whatever our value was at the end of the 3rd year, plus what's happening with our unit cost. So we've done 30,000 kilometres in that 4th year, and each of those kilometres depreciated by 15 cents. Oh, sorry, that actually should be minus. We're depreciating that. So reducing that value. And remember, 15 cents is the same as $0.15. And so when we want to work backwards from there, we've got the 4th year value we know, and we can solve for what was that 3rd year value. And when we do that, we find our value at the end of the 3rd year was $30,666.24. So now I know just for the reducing balance component the change that has occurred. So let's think about setting up an equation for that. If I was to take my initial value 45,000 and I knew my rate, I could set up a general rule. So in general, I would have R, so 1 minus my rate over 100 to the power of n times my initial value, in this case 45,000. So the things I do know is that that value after 3 years was $30,666.24, and therefore n was 3. So when we put that together, 24, 1 minus k over 100, all to the power of 3, times 45,000. I'm now able to solve for k. And so when I do that on my calculator, I get k equals 12. So that gives me the answer B. So 2 big steps here. We had to work backwards from the value that we knew the van ended up at, account for that 1 year of unit cost depreciation to get a value at the end of 3 years. So the value at the end of 3 years. Then we could concentrate on that 3-year period, which was just reducing balance method depreciation, and solve for that rate, which was given to us as K. So just finally, a quick recap of all the rules. They are all basically exactly the same. The biggest thing that we need to check though is what type of geometric movement do we have. If we have growth, we need to make sure that when we're calculating R, are adding that rate to 1. And if we've got decay or depreciation, we're minusing. But our recurrence relations and our general rules are exactly the same for either form. So look for those keywords, check which is the rule that you should use, and go from there. You should be okay.